So in principle, integrals sound like they might be difficult to calculate. So to find the total energy transfer, we need to take like our curve, we need to parameterize it, then we need to like figure out which part of the vector field is perpendicular and which part is parallel, figure out the total contribution from the parallel part, and then compensate, because if we move more quickly through a vector field, we move a further distance per unit time, and more work happens as opposed to if we're moving very, very slowly. And making sure that we do all that sounds like it should be a lot of work. But in fact, arc length integrals are much harder to calculate than line integrals. All we really have to do is if we've got a vector field f, what we do is we take our parameterized curve c of t, we evaluate our vector field at it, and then we take the dot product with the velocity vector. The dot product nicely puts together all the contributions we need from what's the parallel part and how do we calculate the proper compensation for the speed we're moving. It's very, very clean, and that means that line integrals, by contrast with arc-length integrals, tend to be much easier to calculate. In particular, when we had the other type of integral, the path integrals, we would be integrating f of c of t times the length of c of t dt, the speed, and that always involved some kind of square root of sum of squares thing. That's not happening here. We're just taking a dot product. So then we integrate, and if we get a positive number, that means that the object that's moving through gains energy from the vector field, and we get a negative number, it means that the object in net loses energy from the vector field as it's moving through.